Excellent. Okay.
Excellent. Well, welcome everybody, and thank you for attending the talk. Good afternoon, good evening from wherever you are. Quick introduction about myself. I'm Nihanth Cherukuru. I'm a project scientist at NSF-National Center. I come from a multidisciplinary background, actually. Like my PhD was in mechanical engineering, but the focus of my research was mostly with atmospheric fluid mechanics, and I did observation stuff, and then I moved into computational stuff, and eventually the connecting thread for all that was data visualizations. And that's what got me to NCAR. I did some AR, VR stuff with NCAR, and I'll go into the details a little into the talk. So today's talk will be about vapor and a little bit of background at my team at NCAR. So I manage the visualization services and research group at NCAR. In a nutshell, we focus on advanced data visualizations. So there are three areas that we primarily work with, and one of them is software development. Most of us are involved with the development and maintenance of Vapor, and that's what the talk will mostly be about. We also provide visualization support for our scientific staff. So essentially, we work with our scientists and communication folks to use these visualizations as a medium for communication, basically educating the general public about the science that happens at NCAR. And lastly, we also conduct applied research. There are two project scientists in the team, and our focus is mostly on data compression and UX research, basically looking at the human factors with the products and stuff that we develop. It's a new area that we are hoping would play a more pivotal role as we move into the future. Little about Vapor. Vapor is an open source, community-driven interactive application. And most of you might be already familiar with Vapor because it has been around since 2003. It started off as a simple volume renderer, and over a period of time, many more features were added to it. The strength of Vapor is how it's tailored for the geosciences community. There are many other 3D data visualization applications available, but then Vapor really shines in the fact that it has a very simple user interface. It's meant to be, it's basically tailored for the geosciences community, wherein it understands certain data formats that commonly occur in the geosciences. It natively supports those formats, and we have some simple renderers that you can put together and export. It's basically to give the geoscience people working with geoscience data sets a simple workflow from going from their data set to something that they can present or showcase. For a long time, the primary means for us to interact with Vapor has been through a graphical interface, and that's what you see on the left. And the screenshot is from one of our latest versions of Vapor. So in a nutshell, yeah, it has a graphical interface that allows you to do different stuff that we'll get into later. We've been getting a lot of requests about having a scripting interface for Vapor just to expand its functionality. And there was a lot of deliberation on which language to use, and for obvious reasons, we went with Python. So with version 3.7 onwards, we have a Python API that's currently available. The advantage of the Python API is that we can literally do everything that you can see in the GUI within the Python interface. So the video, the screen recording on the right shows me trying to replicate the workflow, the visualization that I did in the graphical interface using the Python API. The video seems to be struggling for some reason. But anyway, yeah, and of course, Vapor supported on most of the modern operating systems. Yeah, and actually one quick bookkeeping stuff. So throughout the talk, I've included some example scripts in that black box somewhere in the slide. Towards the end, and I've also included some screen captures just so that nothing breaks during Zoom, but I'm happy to give a quick demo or walkthrough once everything is done, if you're interested. And of course, over the past 20 years, visualizations produced with Vapor have been featured at multiple places. Those visualizations have also won many awards, and they have been featured in mass media as well as in various journal publications and print publications. If you're interested in looking at more visualizations that were developed with Vapor, the QR code takes us to our YouTube page that has some examples. So moving to the data visualization process, like I remember, like I've mentioned that the strength of Vapor is its usability. So really the data visualization process can be split into like 3 steps. The first step is loading the data. The second step is applying renderers, and renderers are essentially like filters that you apply to the data. And lastly, once you get everything in place, you can then export that to any format that you want to visualize. And I do understand that I might be preaching to the choir when I go into the individual renderers, but just because this talk is recorded, please bear with me as I walk you through some of the features, and I'll try to make it quick. The first step is with loading the data. And this is another strength of Vapor. It supports many data formats that are currently used by the geosciences community right out of the box. So in the GUI, it's all a matter of click of a button. And in the Python API, it's just a one-liner to get your data sets in. So some of the commonly supported data formats are the nets, like CF compliant NetCDF files. We also support I should be clear, like we support layered unstructured grids. So anything that follows the UGrid convention as well as MPAS. And the picture on the right shows an MPAS grid. Of course, binary data, and 2 data formats that are specific to Vapor are the Vapor data collection or the VDC format. VDC was put in place primarily to facilitate interactive exploration of large data sets. So it's a 2-step process. And essentially what you can do is you can use the VDC, some of the tools that we provide with Vapor, to convert your data and compress them. You can save your data in different levels of compression. So after that, what you can do is you can use Vapor to take the highest level of compression, interactively apply different renderers, and like make any changes that you want. And once you're satisfied with it, you can then crank up the compression to like the lowest possible. That's at full fidelity, and then print out whatever you want to print out and showcase. So that's the VDC. And another custom data format that we support is the data collection particles. This is also built on NetCDF, and it's essentially for Lagrangian particle data. So you basically have XYZ values of a certain particle along with Eulerian fields like temperature or something else. And it allows us to, especially we've been seeing lots of particle data sets from the CM1 simulations, for instance. So it allows you to visualize those point clouds or those particles along with the Eulerian fields around it. And especially with the Python API, we can also ingest the data sets from the X-array format, and that is done through a helper function that's provided that translates the X-array data sets into a format that Vapor can understand. And of course, you can learn more about all these things through the QR code that's given here. So the next step is applying the renderers. And yeah, this is another preaching to the choir moment. So if you're someone who's new to 3D visualization, you can make a quick analogy from 2D to 3D. So at its core, the basic process is the same. So you have the data, which is essentially a couple of numbers that are put on a grid, and you're essentially mapping the data onto a color map using a transfer function. The basic methodology is the same, except that in 3D, opacity also plays a major role, mainly because when you're looking something in 3 dimensions, things occlude one another. So the screen recording that you see is basically me applying a transfer function to a renderer, in which you can both control the color as well as the the opacity, and that's the white line that you see in front of the histogram. And this part is common for all the renderers, so I thought I would like put it over here. And of course, like all these things can be done through the Python API, and it's a small like example that I put in at the bottom as to like how you might in this example, like I'm trying to get the opacity values and how that might be applied to a transfer function. So moving on to the renderers, the first one is the volume renderer, and that's also one of the oldest renderer that Vapor had available. Quickly going through what volume rendering is, imagine you have a cube of data. With volume renderer, imagine like from the virtual camera that is painting the picture on the screen, you shoot a laser pulse through each of the pixel that goes through the center of the camera. And along the laser, what you call beam, what we do is we sample the data. And at each of the sample points, we then we map that value to the transfer function that gives us the color. We apply the opacity that's specified, as well as applied lighting. And then we continue doing that for each and every pixel that's present on the screen. And depending on the opacity, as you know, like the colors can like interact with one another, and it gives us like a cloud-like view into your data set. And after that, you can actually control the color maps. You can specify opacities a certain value, and you can really create a visualization that has some resemblance to a physical phenomena. So it's very great for like rendering clouds. And also it's also useful for segmenting certain things in your data if you know what values you're interested in looking at. So that's the volume renderer. Vapor also supports the very basic isosurface renderer. Like I'm contrasting it with contour renderer because like contour renderer is like self-explanatory. It's a very direct, it has a direct analogy to 2D visualization. With Vapor, you have a contour renderer that's a 2D slice, which can be oriented in any way that you want in your domain. Isosurface is like a 3D counterpart to the contour renderer, where like you pick one contour value and render it over the entire space. And with isosurface, again, you are able to encode two variables, like one for the surface and the other for the color on the top of the surface. And of course, separately, you can manually control the opacity to control like what parts you're interested in visualizing. Flor Renderer is slightly more complicated, and it helps us visualize, especially streamlines and path lines. But if you can think of other like vector quantities, you might be able to use it for those. So the image on the left shows the streamlines. So with streamlines, you fix the time step and you create what we call as a rake region. My videos don't seem to be playing, but anyway, I can explain it. So basically you have you seed a couple of values and you propagate streamlines from the initial seed value, as you see in the image. So with streamlines, you fix the time step and it allows you to explore like how the streamlines are laid out in that one particular time step. It's basically simulating like a steady flow. And with path lines, it's similar to like imagine you float some tracers into the flow, and as the flow evolves, you can visualize how these particles travel in time. And the two examples shown here are from Lior. He's one of the power users of Vapor, and he's using this to analyze the flow around a tornado around us. I don't know the details of this data set, but I just know that he's looking at a tornado. And again, I'm not going into the details. It does a lot of other stuff too. As you can see from the image in the top right corner, you can color the individual floor lines by sampling like some other variable on the surface. So you can really examine two variables with this method. And over here, I'm taking a small detour. So with the particle renderer, as I mentioned earlier, like it ingests the data using the DCP format that I've mentioned earlier. And over here, we can represent up to three variables. A, obviously, the location of the particles with the XYZ values that you get from the file. You can also encode uh, another variable using the color of the particles, and also the size of the particles can be used. You can use another variable, a third variable to represent the size of the particles. And this is one of our newer renderers, and this quarter's release will have a major update to particle renderer that has performance improvements and some of the other, like the sizing and color stuff that I've mentioned earlier. And slice renderer is self-explanatory. It's like contour, it's filled. We take every value and map, basically take every value and map it to a color map. You can orient the slice however you want in the 3D domain. Then the next renderer it supports is Barb's. Barb renderer is essentially vector fields. You can use it in 3D as you see on the picture on the top right corner, or we can also have a Barb renderer to be in a 2D mode where you can apply a height variable to it. So you can represent barbs on a terrain. So, and that's what, and this is a visualization that Scott Pierce from my team has created, in which he's showing the surface winds as barbs on top of a terrain. And I won't go into the details of this. So image renderer is what we use to render the image at the bottom. You can also apply a height map to it, so you can accurately represent the terrain underneath. And the images that it takes are geotiffs. And lastly, 2D data renderer is similar to a slice renderer, but the biggest difference is that 2D renderer is oriented horizontally at the bottom of the domain. It's great for capturing variables. Like if you remember the fire example that I've seen, like we represent the burn area using it. And as opposed to the slice renderer, 2D data renderer, you're able to, again, put a height map to it. And yeah, this is just an example where Scott has used like 4 different renderers. So obviously you have the volume renderer that showcases the smoke. You have a 2D data renderer that's showing the burn area. You have the Barb renderer showing surface winds, and the image renderer underneath that has the map. And I believe these 2 are the last renderers. Model renderer can allow you to bring a model into your scene. Like if you want to bring a wind turbine to represent a wind turbine, if you're simulating a wake of a turbine, you can do that. And wireframe renderer is great for examining meshes. So once you import a data, you can, examine a mesh and see like how it looks, or if it has been rendered correctly. And lastly, exporting the data, we can export the data as either image files. You can save an image sequence, or you can save an MP4 to export. And this is where the Python API really shines, wherein you can vastly extend what you can do with the GUI just using the Python API. More specifically, you can do keyframing and camera movements if you use the Python API. So this example was done by a couple of journalists at Straits Times, where what you're seeing is an interactive application that, or rather, it's an interactive article that they've published. The visualization was done in Vapor, but if you see carefully, I seem to be having trouble with my videos. Anyway, so essentially it has a visualization where the camera pans around. So they were one of our first users of the Python API. They used the Python API to first take their visualization and then apply all the camera movements and export it using the functionality that was available with the Python API. And lastly, yeah, the Jupyter widgets. So as you know, if you're in a Jupyter notebook by default, or rather, so when you're working with 3D data visualizations, you have the perception challenge too. You're essentially interpreting something that's 3-dimensional on a 2-dimensional screen. So interaction is something that's almost always necessary when you're working with 3D data sets. To facilitate that, we have a helper module, the Jupyter widgets. It allows us to have some form of interaction, wherein like within the Jupyter notebook, it allows you to drag a box around and see some values, or rather you can change the viewpoint. And it also allows you to create these sliders where in this particular example, I've used a slider to control that slice. So we can slice through the data and see how it appears. I'm not sure if the videos are coming through. They seem to be frozen on my end, but anyway, I'm happy to like walk you through later if you want. So where are we now and what's next? So currently we are at version 3.9. We have a quarterly release going on, and we routinely undertake bug fixes, and training and tutorials is like something that we do on a regular basis. Currently, we have documentation for folks to get started on the Python API and the GUI, but there definitely are some documentation gaps, and we want to address them immediately into the future. There are some major enhancements planned in the near future. The particle renderer improvements that I've mentioned, they are going to come like with this release. We're also planning to have some visualizer enhancements to make it more in line with what some of the other data visualization software has. Like if you take Blender or Paraview or others, to have a similar interface. And we are also working on a universal Linux installer. We've got multiple requests from Linux users where it works on one. We had a separate installer for each version, but we want to have similar. And the Python API and Jupyter Hubs, the Python API does work on Jupyter Hub, but then the widgets don't seem to be working in Jupyter Hub just because of how JavaScript elements with the widgets work. So that's something that we are actively exploring, and we hope to get that functioning by like this quarter or the next. And actually the ones in yellow are the places where like as users and people in the community, like you can really help us out. So currently the Vapor Python, what it does is it takes all the functionality that's available from the GUI and makes them available through the Python API. It works. However, even to do something like a camera panning, like there's a lot of boilerplate code that users have to write before they get to a point that they can visualize. And since all of this would be in Python, I really feel that we could have a separate Python's utilities module that the community can help grow. And especially if you're a domain scientist or someone working in a specific domain, and if there's a certain aspect in your workflow that you feel is recurring, this would be an opportunity to add that to the utilities module, so anyone else who might come in after you can like replicate that workflow. So the everything for it, we are planning to put something in place by Q2 or Q3 of so that this will be like a what do you call a low barrier of entry for anybody who's a Python programmer to start with the Python API, bring in what they might be using in their domain and expand it for the community. And lastly, like as I mentioned, one of the strengths of Vapor is its usability. And we want to extend this moving forward, and we are planning to conduct more user experience research going forward from Q3 onwards. So what this would mean is doing more usability tests or having more interviews with the community, trying to understand like what are their needs and how can those needs be met with a tool like Vapor. And where to go from here, there are a couple of things. Like if you're someone who's interested in contributing to Vapor, like the QR code on the top takes you to the GitHub page. Please join our discourse. And if you have any bug fix, any enhancement requests or something, you'll have an option to add an issue there. Secondly, like if you want to influence the future of Vapor, as I've said, Vapor is community driven and it's open source. I welcome you to join our user research panel. We are still at the beginning stages of this, and the QR code over here takes you to a Google form. And once you put in your information, like we maintain it, so like we are not going to sell your information anywhere. So it creates a database of users that, like let us say in the future, we want to expand on some renderer, or we want to add a functionality for a certain set of domain specialists. We can go through that user pool, and you can reach out to you for maybe having a one-on-one interview or doing a usability test. And lastly, if you're just interested in using Vapor, we like you as well. So the QR code over there, it takes you to the web page that has the project. And last slide, many thanks to all our funding agencies, without which the work wouldn't have been possible. Most of this work is supported by NSF and NCAR. And Vapor's version 3 was largely supported by a grant through KISTI. And I humbly acknowledge the contributions that many people before me have made to Vapor, including John Klein, who's led most of the Vapor development until like an year or two ago. And also numerous software engineers and students who took Vapor from an initial volume renderer to what it is right now. And special thanks to steering committee and Leorf. So the examples that I've shown earlier, those data sets are from Leorf. So many thanks to him. And last but not the least, the development team. I'm just a messenger over here. Like most of the work and the documentation, everything that you see in Vapor currently, that's managed by a team of 3 people. So like I really appreciate like the 3 team members. And I believe Stanisław Jarosinski, or Stosh, he's currently serving as the chief architect for Vapor. He's on the call. If you have any technical questions related to Vapor, he'll be able to answer those. And yeah, thanks to you all for attending the talk. And we also have a Vapor Python cookbook at Project Pythia. So if you want to like try something out, like that's another like, option to explore. So with that, I'm happy to take any questions.
All right, great. Thank you, Nihanth. I'm going to stop the recording. And